Tonight, we're going to talk about a particle that should not exist by the time it reaches you. Right now, as you're listening to this, thousands of tiny unstable particles are passing through your body every single minute. They were born high above the Earth, about 10 miles up, created in violent collisions at the top of our atmosphere. And here's the problem. These particles die fast. They live for roughly 2 millionths of a second. At that lifespan, even moving close to the speed of light, they should disintegrate long before they ever reach the ground. The math says they can't make it. And yet, they do. They reach the surface in enormous numbers. And the reason they survive is one of the most stunning confirmations of something Einstein predicted. Time itself is slowing down for them. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Right now, as you're sitting here, something extraordinary is happening to your body. Tiny particles, smaller than atoms, are raining down from the sky and passing straight through you. Not a few of them, not occasionally. About 10,000 of them are hitting every square meter of Earth's surface every single minute. They're passing through the roof above your head, through your skin, through your bones, through the floor beneath your feet, and continuing down into the ground below. You don't feel them. You can't see them, but they are there. And they have been there every second of every day for as long as the Earth has existed. These particles are called muons, and their existence at ground level is one of the most quietly astonishing facts in all of physics. Not because muons themselves are unusual. Subatomic particles are everywhere. The universe is full of them. What makes muons extraordinary is that they should not be reaching you at all. They should be dying long before they ever get close to the surface of the Earth. Everything we know about how fast they move and how quickly they decay says that muons created high in the atmosphere should disintegrate into other particles well before they reach the ground. And yet, they don't. They survive. They make it all the way down. They pass through your body by the millions every single day. And the reason they survive, the reason they are able to make a journey that classical physics says is impossible, is one of the most beautiful and unsettling truths about the universe we live in. Time is not passing at the same rate for them as it is for you. But before we can understand why that matters, we need to understand where these muons come from in the first place. And that story starts not on Earth, but in the deepest reaches of outer space. The universe is a violent place. It might not seem like it when you look up at a calm, quiet night sky. The stars seem peaceful. Space seems still. But that serenity is an illusion created by distance. Out there, across the cosmos, some of the most extreme events imaginable are happening constantly. Stars are exploding, black holes are tearing matter apart, neutron stars are colliding with each other in bursts of energy so intense they briefly outshine entire galaxies, and remnants of exploded stars are accelerating charged particles to almost unimaginable speeds through mechanisms we still don't completely understand. These particles, mostly protons but also heavier atomic nuclei, are flung out into space at velocities approaching the speed of light. They travel for millions or even billions of years across the vast emptiness between stars and galaxies, crossing unimaginable distances, carrying enormous amounts of energy packed into something smaller than a trillionth of a meter. These are cosmic rays, And they are everywhere. They fill the galaxy. They permeate interstellar space. They have been streaming through the universe since the first stars began to die. Some of them carry more energy in a single particle than a professionally served tennis ball carries in its entire motion across a court. One cosmic ray detected in 1991, nicknamed the "Oh my God" particle, carried an energy of about 320 million trillion electron volts. To put that in perspective, this was a single subatomic particle, invisible to the naked eye, carrying roughly the same kinetic energy as a baseball thrown at about 60 miles per hour. All of that energy concentrated in one proton. That is an almost incomprehensible amount of energy for something so small. We still don't know exactly what process in the universe can accelerate a single particle to that kind of speed. But we know these particles exist because they hit us constantly. Earth is bathed in cosmic rays. Every second of every day, cosmic ray particles rain down on our atmosphere from every direction. Some come from the sun, some come from within our galaxy. Some come from far beyond, from distant galaxies and unknown sources. They arrive at all energies, from relatively modest to absolutely extreme. Most of the cosmic rays hitting Earth's atmosphere are protons, the nuclei of hydrogen atoms. About 90% are protons. Another 9% are alpha particles, helium nuclei made of 2 protons and 2 neutrons. The remaining roughly 1% are heavier nuclei, atoms of carbon, oxygen, iron, and other elements stripped of their electrons and accelerated to tremendous speeds. A cosmic ray proton might have been ejected from a supernova explosion millions of years ago in another part of the galaxy. It has been flying through the interstellar medium ever since, deflected by magnetic fields, bouncing through the galaxy like a pinball until one day, purely by chance, its path intersects with a small rocky planet orbiting an ordinary star, Earth. When a cosmic ray proton arrives at Earth, it doesn't just gently drift down through the atmosphere. It slams into it. The atmosphere might seem thin and insubstantial when you're standing on the ground breathing it in, but from the perspective of a particle arriving from space, the atmosphere is a wall of matter. Earth's atmosphere extends up to about 100 kilometers, but the bulk of the dense air is concentrated in the lowest 15 to 20 kilometers. When a high-energy cosmic ray proton hits the top of the atmosphere, it collides with the nucleus of a nitrogen or oxygen atom. These are the 2 most common gases in our atmosphere. Nitrogen makes up about 78% of the atmosphere, and oxygen makes up about 21%. The incoming cosmic ray proton is traveling at very close to the speed of light. The nitrogen or oxygen nucleus it hits is essentially stationary by comparison. The collision is extraordinarily violent on a subatomic scale. The energy involved is enormous, and when that much energy is concentrated into a collision between subatomic particles, something remarkable happens. New particles are created. This is one of the most profound consequences of Einstein's famous equation relating energy and mass. Energy can be converted into matter. When enough energy is present in a collision, that energy can materialize as entirely new particles that didn't exist before the collision. The incoming cosmic ray had kinetic energy. That kinetic energy gets converted into mass and kinetic energy of new particles. It is like smashing 2 billiard balls together so hard that the impact creates 10 new billiard balls that fly off in every direction. That doesn't happen with actual billiard balls, of course, but in the subatomic world, at these energies, it happens all the time. The first collision between the cosmic ray proton and an atmospheric nucleus produces a spray of particles. These are mostly pions. Pions are a type of subatomic particle, part of a family called mesons. They come in 3 varieties: positively charged pions, negatively charged pions, and neutral pions. A single high-energy cosmic ray collision can produce dozens of pions, along with other particles. This initial burst of particles is just the beginning, because each of those newly created particles is itself moving at tremendous speed, carrying a portion of the original cosmic ray's energy. And when those secondary particles hit other atmospheric nuclei, they create even more particles. And those particles hit more nuclei, creating still more particles. The result is what physicists call an extensive air shower. A single cosmic ray proton hitting the top of the atmosphere can trigger a cascade of secondary particles that multiplies as it descends. A single high-energy cosmic ray can produce millions or even billions of secondary particles by the time the shower reaches the ground. The shower spreads out as it descends, forming a cone-shaped cascade of particles raining downward through the atmosphere. The neutral pions created in these collisions are important because they decay almost instantly into pairs of high-energy photons called gamma rays. These gamma rays then produce pairs of electrons and positrons, which produce more gamma rays, which produce more electron-positron pairs, creating an electromagnetic cascade alongside the particle cascade. The atmosphere is essentially being lit up by a chain reaction of particle creation and destruction triggered by a single cosmic ray arriving from space. But for our story, the most important particles in this cascade are not the pions themselves. They are what the charged pions turn into when they decay. And this is where the muon enters the picture. Charged pions are unstable. They don't last long. A charged pion has a mean lifetime of about 26 billionths of a second. That's incredibly short. Almost as soon as a charged pion is created, it decays. And when a charged pion decays, it transforms into a muon and a muon neutrino. The positively charged pion decays into a positive muon and a muon neutrino. The negatively charged pion decays into a negative muon and a muon anti-neutrino. This happens high in the atmosphere, typically at altitudes of about 15 kilometers or roughly 9 to 10 miles above the surface. This is the altitude where most of the cosmic ray collisions take place because that's where the atmosphere has become dense enough for collisions to be common. So right now, at this very moment, high above your head, roughly 15 kilometers up in the sky, cosmic ray collisions are producing enormous numbers of pions, and those pions are almost immediately decaying into muons. These muons are the particles that concern us. These muons are being created at tremendous speeds, typically about 99.95% the speed of light. They're created heading downward toward the Earth's surface, carrying some of the enormous energy from the original cosmic ray collision. And it is these muons that somehow manage to reach the ground in huge numbers, passing through your body by the thousands every minute. Now, let me tell you what a muon actually is, because understanding its nature is essential to understanding why its survival is so shocking. A muon is an elementary particle. That means it's not made of anything smaller, at least as far as we know. It's one of the fundamental building blocks of matter. It belongs to a family of particles called leptons. Electrons are also leptons. In fact, a muon is essentially a heavier version of the electron. It carries the same negative electrical charge as an electron. It behaves like an electron in almost every way. It interacts through the same forces. The only major difference is mass. A muon is about 207 times heavier than an electron. If an electron weighed 1 kilogram, a muon would weigh 207 kilograms. Same charge, same type of particle, but much, much heavier. And here is the crucial thing. Unlike the electron, which is stable and can exist forever as far as we know, the muon is unstable. It decays. Every muon that is created will eventually fall apart into other particles. A muon decays into an electron, a muon neutrino, and an electron antineutrino. This decay is inevitable. It's built into the nature of the particle. You can't prevent it. You can't slow it down by cooling the muon, or isolating it, or putting it in some special container. The decay is governed by the weak nuclear force, one of the 4 fundamental forces of nature, and it happens on a fixed timescale that is a property of the muon itself. That timescale is extremely short. The mean lifetime of a muon is about 2.2 microseconds. A microsecond is 1 millionth of a second. So 2.2 microseconds is 2.2 millionths of a second. To give you a sense of how brief that is, consider that a blink of your eye takes about 300,000 to 400,000 microseconds. In the time it takes you to blink once, about 150,000 to 180,000 muon lifetimes have passed. A muon's entire existence, from the moment it's created to the moment it decays, fits into a span of time so short that no human sense could ever detect it. You could never perceive it. If you snap your fingers, roughly 100,000 muon lifetimes would pass during the sound of that snap. This is important because it creates a problem, a very serious problem. Let's do some straightforward math. This is the calculation that makes the muon's arrival at ground level seem impossible. And I want to walk through it slowly so you can see exactly why physicists were so puzzled. A muon is created at an altitude of about 15 kilometers above the Earth's surface. That's 15,000 meters. The muon is traveling at about 99.95% of the speed of light. The speed of light is roughly 300,000 kilometers per second, or 300 million meters per second. 99.95% of that is about 299,850,000 meters per second. The muon lives for about 2.2 microseconds. That's 2.2 millionths of a second, or in decimal terms, 0.00000022 seconds. Now, how far can something travel if it's moving at 299,850,000 meters per second for 2.2 millionths of a second? You multiply the speed by the time. The answer is about 660 meters. 660 meters. That's roughly the length of 6 or 7 football fields. If you stood at one end of a long straight road and looked about 660 meters down that road, that's how far a muon should be able to travel in its lifetime, even moving at nearly the speed of light. 660 meters. But the muon was created 15,000 meters above the ground. That's more than 22 times farther than the muon can travel before it decays. This is like telling someone they need to run a marathon, but they can only survive for the first mile. The muon is born with a destination it can never reach. By the time it has traveled 660 meters, its internal clock has run out. It should decay into an electron and 2 neutrinos, vanishing from existence more than 14 kilometers above your head. And it's not just a matter of 1 or 2 muons dying early. The mathematics of particle decay are exponential. After one lifetime, about 63% of the original muons have decayed. After 2 lifetimes, about 86% are gone. After 5 lifetimes, more than 99% have vanished. The journey from 15 kilometers to sea level, at the speed these muons travel, takes about 50 microseconds. That's roughly 23 muon lifetimes. After 23 lifetimes, the fraction of muons that should survive is essentially 0. Not close to 0. Not a tiny number. Essentially 0. If you started with 10,000 muons at the top of the atmosphere, the classical prediction says that by the time they've traveled 15 kilometers, fewer than 1 out of every billion should still exist. The number that should reach the ground is so small that for all practical purposes, it might as well be 0. You should almost never detect a muon at sea level. Ground-based detectors should be silent. The muons should all be gone, decayed into electrons and neutrinos long before they get anywhere near the surface. But it's not what happens. That's not what happens at all. When physicists actually place detectors at sea level and count the muons arriving from the atmosphere, they don't find 0. They don't find a trickle, they find a flood. The measured muon flux at sea level is roughly 10,000 muons per square meter per minute. 10,000 every minute through every square meter of the Earth's surface. That is an enormous number. It means that right now, at this moment, muons are pouring through you, through the building you're in, through the ground beneath you in vast quantities. They're arriving at a rate that the classical calculation says is flatly impossible. The classical picture, the straightforward calculation using the muons' known lifetime and known speed, predicts almost none of them should make it. And yet, there they are. Thousands upon thousands of them, raining down continuously. Something in the classical calculation must be wrong. Not the speed. We can measure that. Not the altitude where muons are created. We can measure that too. Not the muons' lifetime as measured in a laboratory at rest. That has been measured with extraordinary precision. Every ingredient in the calculation is correct individually. And yet the prediction is catastrophically wrong. There must be something missing. Some piece of physics that the straightforward calculation doesn't account for. Something that allows muons to survive a journey that simple arithmetic says they cannot complete. This was one of the great puzzles of 20th century physics. The muon was discovered in 1936 by Carl Anderson and Seth Neddermeyer while studying cosmic ray tracks in a cloud chamber. They found a particle that didn't match anything known at the time. It was heavier than an electron, but lighter than a proton. It carried an electric charge, and it showed up in cosmic ray showers with surprising frequency. At first, physicists thought they had found something that had been predicted just the year before. In 1935, the Japanese physicist Hideki Yukawa had proposed a theory of the strong nuclear force, the force that holds protons and neutrons together inside atomic nuclei. Yukawa's theory predicted that this force should be carried by a particle with a mass between that of the electron and the proton. When Anderson and Neddermeyer found their new particle with a mass in roughly that range, excitement spread through the physics community. They believed they had discovered Yukawa's predicted carrier of the nuclear force. But something was wrong. If this particle was truly the carrier of the strong nuclear force, it should interact powerfully with atomic nuclei. That's the whole point of a nuclear force carrier. It should be absorbed by nuclei. It should be scattered by them. It should have trouble passing through matter because it should be constantly interacting with the nuclei of every atom it encounters. But the particle Anderson and Neddermeyer found didn't do this at all. It passed through matter with remarkable ease. It sailed through blocks of iron, as though the nuclei inside weren't even there. It barely interacted with anything. This was deeply confusing. The particle had roughly the right mass to be Yukawa's meson, but it had completely the wrong behavior. It was like finding a key that's the right size for a lock, but refuses to turn. Experiments in the late 1940s, particularly those by Marcello Conversi, Ettore Pantini, and Oreste Piccioni in Rome, made this contradiction undeniable. They showed that even when negative muons were stopped inside matter, surrounded by atomic nuclei, they still mostly just sat there and decayed on their own rather than being captured by the nuclei. The interaction rate was absurdly low for a particle that was supposed to carry the strong nuclear force. The puzzle was finally resolved in 1947 when Cecil Powell and his team at the University of Bristol discovered the actual particle Yukawa had predicted. They called it the pion. The pion was a different particle entirely, slightly heavier than the muon, and it interacted strongly with nuclei exactly as Yukawa's theory required. It turned out that pions were created in the initial cosmic ray collisions, and then quickly decayed into muons. The particle Anderson and Neddermeyer had found wasn't Yukawa's force carrier at all. It was a decay product of the real force carrier. The muon was something else entirely, something unexpected, something that didn't seem to fit into the neat theoretical framework of the time. It had no obvious role in holding nuclei together. It didn't carry any known force. It was just there. A heavier copy of the electron, with no apparent purpose. The Nobel Prize-winning physicist Isidore Isaac Rabi, upon learning that the muon was not Yukawa's particle, but something entirely new and unexplained, reportedly responded with a question that became one of the most famous lines in the history of particle physics. He asked simply, "Who ordered that?" Nobody had predicted the muon. Nobody needed it. It didn't solve any existing puzzle. It was a particle that showed up uninvited, and nobody knew why it existed. Decades later, we still don't fully understand why the muon exists. Why nature created what appears to be a heavier duplicate of the electron. But we do know that its existence, and particularly its puzzling survival, as it races through the atmosphere, opened the door to one of the most stunning confirmations in the history of science. When the muon's short lifetime was measured, physicists immediately realized there was another problem on top of the identity crisis. The muons being detected at ground level were arriving in numbers that didn't make sense. The particles were too short-lived to survive the trip from the upper atmosphere to the surface. And yet, detectors kept counting them. The data was unambiguous. The muons were there. You could see their tracks. You could count them. You could measure their energies. There was no question that they were arriving at ground level in enormous quantities. But the math said they couldn't. For a while. This was genuinely confusing. Some physicists wondered if muons were being created lower in the atmosphere than previously thought. Maybe they weren't being born at 15 kilometers. Maybe they were being created much closer to the ground, which would give them less distance to travel. But careful measurements of the cosmic ray cascade ruled this out. The collisions that create pions, and therefore muons, really do happen at high altitudes. The atmosphere isn't dense enough at lower altitudes to produce the kinds of collisions that generate muons in large numbers. Other physicists wondered if there was something wrong with the lifetime measurements. Maybe muons lived longer than 2.2 microseconds. But laboratory measurements were clear. When you create muons at rest in a lab and watch them decay, they die with a mean lifetime of about 2.2 microseconds. There was no wiggle room. The speed was right. The distance was right. The lifetime was right. Every piece of the puzzle was individually correct. And yet, when you put them together, the prediction failed spectacularly. The answer to this puzzle had actually been predicted decades before the muon was even discovered. In 1905, a young physicist working as a patent clerk in Switzerland had published a paper that would change everything we thought we knew about space, time, and the nature of reality itself. His name was Albert Einstein, and his theory of special relativity contained a prediction so strange, so counterintuitive, that even Einstein himself found it unsettling. The prediction was this: time does not pass at the same rate for everyone. A clock that is moving relative to you will tick slower than your own clock. The faster it moves, the slower it ticks, and at speeds close to the speed of light, this effect becomes enormous. This is not a metaphor. It's not poetry. It's not some vague philosophical idea about how time feels different when you're busy versus when you're bored. This is a literal, physical, measurable slowing down of time itself. Moving clocks run slow. Moving particles age slower. Moving hearts beat fewer times. Everything that happens in a moving reference frame happens more slowly when observed from the outside. And a muon traveling at 99.95% of the speed of light is moving fast enough for this effect to be dramatic. From our perspective here on the ground, watching that muon streak downward through the atmosphere, the muon's internal clock is running much slower than our clocks. Its 2.2 microsecond lifetime, as measured by its own internal processes, gets stretched out enormously as observed by us. The muon thinks it's living for 2.2 microseconds, but to us, watching from the ground, it appears to live far longer, long enough to traverse 15 kilometers, long enough to reach the surface, long enough to pass through your body. The muon doesn't break any laws of physics. It doesn't cheat death. It doesn't exceed the speed of light or find some shortcut through the atmosphere. It simply exists in a universe where time itself is flexible, where time runs at different rates depending on how fast you're moving. And because of that flexibility, because of that strange and wonderful property of the universe, muons survive a journey that classical physics says is impossible. This is not a small correction. This is not a minor adjustment to the numbers. Without time dilation, virtually no muons should reach the ground. With time dilation, thousands per square meter per minute arrive. The difference between the classical prediction and the observed reality is not a factor of 2 or 10. It's a factor of billions. Time dilation is not a subtle effect when it comes to muons. It is the entire explanation. Without it, the world would be measurably different. The muon flux at ground level would be essentially zero. Particle detectors at the surface would sit in silence. And one of the most beautiful confirmations of Einstein's theory would never have been noticed. But time dilation is real. The muons do arrive. And every single one of them, every muon that passes through your body right now, is a tiny messenger carrying proof that time does not work the way your intuition tells you it should. The universe is stranger than it appears, And a particle that lives for barely 2 millionths of a second is the one that proves it. To understand why muons survive their impossible journey, we need to understand something that most people think they understand, but actually don't. We need to understand time. And I mean really understand it. Not the everyday version of time that you experience when you glance at a clock or wait for a bus or count down the seconds until the weekend. I mean the actual physical nature of time itself, what it is, how it works, and why it doesn't behave the way you think it does. Because here's the truth. For almost all of human history, we had time completely wrong. We thought we understood it. We built clocks to measure it. We divided it into hours and minutes and seconds. We assumed it was simple, universal, and absolute. And every single one of those assumptions turned out to be incorrect. The story of how we discovered this begins in the late 1800s, at a time when physics seemed almost complete. Scientists had figured out the laws of motion thanks to Isaac Newton. They had figured out the laws of electromagnetism thanks to James Clerk Maxwell. They had built a framework that could predict the motion of planets, the behavior of magnets, the properties of light, and the interactions of charged particles. Physics seemed almost finished. There were just a few small problems left to clean up, a few loose ends that didn't quite fit. Most physicists at the time assumed these loose ends would be resolved quickly with minor adjustments to existing theories. They were spectacularly wrong. Those loose ends would demolish the entire framework of classical physics and force humanity to completely reimagine the nature of space, time, and reality. One of those loose ends involved light. By the late 1800s, Maxwell's equations had shown that light is an electromagnetic wave. It's a ripple in electric and magnetic fields that propagates through space at a specific speed. That speed, about 300,000 kilometers per second, fell naturally out of Maxwell's equations. It wasn't something you had to put in by hand. It emerged automatically from the mathematics of electromagnetism. But this created a puzzle. 300,000 kilometers per second relative to what? When you say a car is moving at 100 kilometers per hour, you mean relative to the ground. When you say a plane is moving at 900 kilometers per hour, you mean relative to the air or the ground below it. Every speed is measured relative to something. So when Maxwell's equation said light moves at 300,000 kilometers per second, the natural question was relative to what? At the time, physicists assumed light must travel through some kind of medium, just like sound travels through air and water waves travel through water. They called this hypothetical medium the luminiferous ether. The idea was that the ether filled all of space and light was a vibration in this ether. The speed of light in Maxwell's equations would then be the speed relative to the ether. This seemed reasonable, but it made a testable prediction. If the ether exists, and if the Earth is moving through it as it orbits the sun, then the speed of light should be slightly different depending on which direction you measure it. Like swimming with or against a current, light should appear faster in one direction and slower in the other. The difference would be small, because Earth's orbital speed is only about 30 kilometers per second. Tiny compared to light's 300,000. But it should be measurable. In 1887, two American physicists, Albert Michelson and Edward Morley, built an extraordinarily precise instrument called an interferometer to detect this difference. Their device split a beam of light into two paths at right angles to each other, sent each beam out and back along its path, and then recombined them. If the speed of light was different in different directions due to Earth's motion through the ether, the two beams would arrive back slightly out of sync and create an interference pattern that could be detected. Michelson and Morley performed their experiment with painstaking care. They repeated it multiple times. They tried it at different times of year when Earth was moving in different directions through its orbit, and they found nothing. Absolutely nothing. No difference in the speed of light in any direction. The result was always the same. Light appeared to travel at exactly the same speed, regardless of which direction it was going, regardless of how Earth was moving. This was baffling. It was as if you were running on a moving train and threw a ball forward, and someone on the ground measured the ball's speed and found it was exactly the same whether the train was moving or standing still. That makes no sense in everyday experience. Speeds should add up. If you're on a train moving at 50 kilometers per hour and you throw a ball forward at 20 kilometers per hour, someone on the ground should see the ball moving at 70 kilometers per hour. That's just basic addition. But light didn't follow this rule. No matter how fast you were moving, light always traveled at exactly the same speed. 300,000 kilometers per second. No more, no less, always. This single experimental result, this failure to detect any change in the speed of light, was one of those loose ends that would destroy classical physics. For nearly 2 decades, physicists struggled to explain the Michelson-Morley result. Some proposed that the ether was somehow dragged along by the Earth, eliminating the expected difference. Others suggested the ether existed but was undetectable for subtle reasons. The Dutch physicist Hendrik Lorentz and the Irish physicist George Fitzgerald independently proposed that objects moving through the ether physically contracted in the direction of motion by just the right amount to cancel out the expected effect. These were clever ideas, but they felt like patches. They were attempts to save the ether by adding special rules to explain why it couldn't be detected. The explanations worked mathematically, but they didn't feel right. They didn't explain why nature would conspire to hide the ether so perfectly. Then, in 1905, a 26-year-old patent clerk in Bern, Switzerland, published a paper that solved the entire problem in a way nobody expected. His name was Albert Einstein, and instead of trying to save the ether or patch up the old theories, he threw the whole framework out and started over with 2 remarkably simple statements. These 2 statements are the postulates of special relativity. The first postulate says that the laws of physics are the same in all inertial reference frames. An inertial reference frame is just a fancy way of saying any observer who isn't accelerating. If you're floating in deep space with no forces acting on you, you're in an inertial frame. If you're riding in a train moving at constant speed on a straight track, you're in an inertial frame. The first postulate says that no experiment you perform inside your reference frame can tell you whether you're moving or stationary. Physics works the same way regardless. This postulate wasn't new. Galileo had proposed something similar centuries earlier. The second postulate was the revolutionary one. It says that the speed of light in a vacuum is the same for all observers, regardless of their motion or the motion of the light source. This is the one that changes everything. It says that no matter how fast you're moving, when you measure the speed of a beam of light, you will always get exactly the same number, 300,000 kilometers per second. It doesn't matter if you're standing still. It doesn't matter if you're moving toward the light at half the speed of light. It doesn't matter if you're moving away from the light at 90% of the speed of light. you will always measure the same speed. This sounds impossible. It violates everything your intuition tells you about how speeds work. If I'm standing still and I see a beam of light passing me at 300,000 kilometers per second, and you're chasing that same beam at half the speed of light, surely you should measure the light as moving at only 150,000 kilometers per second relative to you. The light should appear slower to you because you're partially keeping up with it. But Einstein said no. You would also measure the light at 300,000 kilometers per second. Both of us, despite moving at very different speeds, would measure the exact same speed for the light. This seems like a contradiction. It seems like it can't possibly work. If we both measure the same speed for the light, but we're moving at different speeds ourselves, something has to give. Something about our measurements must be different. And Einstein realized what that something was. It was time itself. Let me show you why the constancy of the speed of light forces time to behave strangely. Imagine you build a simple clock, the simplest clock imaginable. You take two mirrors and place them facing each other, one above the other, separated by a fixed distance. Then you bounce a single pulse of light back and forth between the two mirrors. Every time the light pulse hits the bottom mirror, the clock ticks. This is called a light clock, and it's a standard thought experiment in relativity. The beauty of this clock is that its ticking rate depends on only two things: the distance between the mirrors and the speed of light. Since both of those are well defined, the clock ticks at a completely predictable, steady rate. Now, imagine this light clock is sitting on a table in front of you. The light bounces straight up and down between the two mirrors. Up, down, tick, up, down, tick. Each round trip takes a certain amount of time that depends on the distance between the mirrors. Simple. Now imagine someone puts this light clock on a spaceship that's moving past you at a very high speed. Let's say 60% of the speed of light. You're standing on the ground watching the spaceship fly by, and through a window you can see the light clock inside. From the perspective of the person on the spaceship, nothing has changed. The light clock is sitting still relative to them. The light bounces straight up and down. Up, down, tick, up, down, tick. The clock works exactly the same as it always did. But from your perspective on the ground, something is different. The spaceship is moving. And because the spaceship is moving, the bottom mirror has shifted position by the time the light pulse comes back down from the top mirror. From your point of view, the light isn't bouncing straight up and down. It's bouncing along a diagonal path. It goes up and to the right, hits the top mirror, then comes back down and to the right to hit the bottom mirror, which has moved forward during the time the light was in transit. The light is tracing a zigzag pattern instead of a straight vertical line. Here is the critical insight. The diagonal path is longer than the straight vertical path. Think about it geometrically. If the light goes straight up and down, it travels a certain distance. But if it goes diagonally up and to the right, then down and to the right, it travels a greater distance. The diagonal of a triangle is always longer than either of its sides. And now remember Einstein's second postulate. The speed of light is the same for everyone. The person on the spaceship measures the light moving at 300,000 kilometers per second. And you, standing on the ground, also measure that same light moving at 300,000 kilometers per second. Not faster, not slower, exactly the same speed. But here's the problem. You're watching the light travel a longer path, the diagonal path, and you're measuring it traveling at the same speed as always. If something travels a longer distance at the same speed, it must take more time. This is inescapable. Distance equals speed multiplied by time. If the distance is longer and the speed is the same, the time must be greater. From your perspective on the ground, the light clock on the moving spaceship takes longer to complete each tick. The clock is running slower. Not because it's broken, not because something is wrong with it, but because the light inside it has to travel a longer path due to the motion of the ship. And since the speed of light is fixed and cannot increase to compensate, each tick simply takes longer. This is time dilation. A moving clock runs slower than a stationary clock. And it's not just this particular type of clock. It's every clock. It's every process. It's time itself. Because if you replace the light clock with a mechanical clock, or an atomic clock, or a biological process like the beating of a heart, and the light clock on the same spaceship was running slow, but some other clock on the same spaceship was keeping normal time, then the two clocks on the spaceship would disagree with each other. The person on the spaceship could compare them and notice the discrepancy. And that would violate Einstein's first postulate, which says physics must work the same way on the spaceship as it does on the ground. If physics works the same way on the spaceship, then all clocks on the spaceship must agree with each other. They must all tick at the same rate relative to each other. And since we've shown that the light clock must run slow when observed from the ground, all clocks on the spaceship must run slow when observed from the ground. Everything on the spaceship ages slower. The clocks tick slower. The hearts beat slower. Chemical reactions proceed slower. Radioactive atoms decay slower. Every physical process, without exception, runs slower on the moving spaceship as observed from the ground. Now, let me be very precise about something because this is where people often get confused. The person on the spaceship does not notice anything strange. From their own perspective, time is passing completely normally. Their clocks tick at the normal rate. Their hearts beat at the normal rate. They don't feel like they're moving in slow motion. Everything on the spaceship feels perfectly ordinary. The slowing of time is only apparent to someone watching from a different reference frame. When you stand on the ground and observe the spaceship, you see their clocks running slow, but from their perspective, standing on the spaceship and looking out the window at you, they would see your clocks running slow. This isn't a contradiction. It's a fundamental feature of relativity. Each observer sees the other's clocks running slow because each observer's light clock traces a diagonal path from the other's perspective. This symmetry is built into the theory. Neither observer is wrong. Neither perspective is more correct than the other. Both are equally valid. This is what physicists mean when they talk about the relativity of time. Time is not absolute. It does not tick at the same rate for everyone. Two observers moving relative to each other will measure time passing at different rates, and both of their measurements are correct. There is no universal clock somewhere in the universe keeping the one true time. Time is relative depending on your state of motion. The amount by which time slows down depends on how fast you're moving. At everyday speeds, the effect is incredibly tiny, almost non-existent. If you drive your car at 100 kilometers per hour, time slows down for you by about 0.0000000000004%. That's so small that no clock on Earth could measure it. For all practical purposes at everyday speeds, time dilation doesn't exist. You'll never notice it. But as you approach the speed of light, the effect grows dramatically. The relationship between speed and time dilation is captured by something called the Lorentz factor, often represented by the Greek letter gamma. You don't need to understand the math to grasp the concept. What matters is the pattern. At 10% of the speed of light, gamma is about 1.005. Time is running only about 0.5% slower. At 50% of the speed of light, gamma is about 1.15. Time is running about 15% slower. At 90% of the speed of light, gamma is about 2.3. Time is running more than twice as slow. At 99% of the speed of light, gamma is about 7.1. Time is running about 7 times slower. At 99.9% of the speed of light, gamma is about 22.4. Time is running more than 22 times slower. At 99.99% of the speed of light, gamma is about 70.7. Time is running more than 70 times slower. Notice how the effect accelerates. Going from 0 to 90% of light speed only gives you a factor of about 2. But going from 99% to 99.99%, just a tiny increase in speed, gives you a factor of about 70. The closer you get to the speed of light, the more dramatically time slows down. And as you approach the speed of light itself, gamma approaches infinity. Time would stop altogether at the speed of light, which is one of the reasons nothing with mass can ever reach the speed of light. It would require infinite energy, and time would cease to pass. This leads to two important concepts that are worth understanding clearly. The first is called proper time. This is the time measured by a clock that is traveling with the object in question. It's the time experienced by the object itself. For a muon, proper time is the 2.2 microseconds that represents its lifetime, as measured by a clock riding along with the muon. From the muon's own perspective, it lives for 2.2 microseconds. Period. That doesn't change regardless of how fast the muon is moving. The muon always experiences 2.2 microseconds of existence. The second concept is coordinate time. This is the time measured by an observer in a different reference frame. For us, standing on the ground, watching a muon streak through the atmosphere, coordinate time is what our clocks measure for the duration of the muon's existence. And because of time dilation, our clocks will measure a much longer duration than 2.2 microseconds. The muon's proper time is 2.2 microseconds. Our coordinate time for the muon's life is much longer. Both measurements are correct. Both are real. They're just measured in different reference frames. This distinction between proper time and coordinate time is absolutely essential for understanding the muon's survival. The muon always lives for 2.2 microseconds in its own frame, but from our frame, it lives much longer. And that extra time, that stretching of the muon's apparent lifetime as seen from the ground, is what allows it to traverse 15 kilometers of atmosphere and reach the surface. Now, I want to emphasize something that cannot be stated too strongly. Time dilation is not a theoretical prediction still waiting to be tested. It is one of the most thoroughly confirmed facts in all of physics. It has been measured directly using atomic clocks, observed routinely in particle accelerators, and built into the engineering of technologies you use every single day. We'll get into the specific experiments later, because they deserve careful attention. But for now, know this. Time dilation is not speculation. It is observed fact, confirmed to extraordinary precision across more than a century of experiments. It is as solidly established as gravity, what deserves more attention here is why you can't just speed up to avoid the problem altogether. Why can't we simply accelerate something to the speed of light? If time slows down as you go faster, and it stops completely at light speed, why not just get there? The answer reveals something deep about the relationship between energy and speed at relativistic velocities. In everyday life, if you want something to go faster, you push it harder. You add energy. A car going 50 kilometers per hour needs a certain amount of fuel to accelerate to 100. It needs roughly the same additional amount to go from 100 to 150. The relationship feels proportional. Double the speed, roughly quadruple the energy, because kinetic energy scales with the square of the velocity. But this linear feeling relationship between effort and speed is an approximation that only works at slow speeds. As an object approaches the speed of light, the amount of energy required to make it go even slightly faster increases dramatically. Not linearly, not quadratically. It increases without limit. At 90% of the speed of light, a particle needs about 2.3 times more energy than its rest mass energy to maintain that speed. At 99%, it needs about 7 times more. At 99.9%, it needs about 22 times more. At 99.99%, it needs about 71 times more. Each additional fraction of a percent closer to light speed costs more energy than everything that came before it combined. The energy doesn't just increase, it diverges. It heads toward infinity. To actually reach the speed of light, you would need literally infinite energy. Not a very large amount, not an astronomically large amount. Infinite. And infinite energy doesn't exist. There isn't enough energy in the entire observable universe to accelerate a single proton to exactly the speed of light. This is not an engineering limitation. It's not a problem we can solve with better rockets or more powerful engines. It's a fundamental law of nature woven into the structure of space-time itself. The speed of light is not just a speed, it's a boundary, a wall built into the fabric of the universe that nothing with mass can ever cross. This is why massless particles like photons, which are particles of light, always travel at exactly the speed of light. They have no mass, so they don't face this infinite energy barrier. In fact, photons must travel at the speed of light. They can't slow down. They can't speed up. From the moment they're created to the moment they're absorbed, they travel at exactly 300,000 kilometers per second. For a photon, time doesn't pass at all. If a photon could experience anything, its creation and its absorption would happen at the same instant, regardless of how far it traveled. A photon that crosses the entire observable universe experiences zero elapsed time. This is why the speed of light occupies such a unique place in physics. It's not just the speed that light happens to travel at. It's the speed at which time stops. It's the universal speed limit, not because nothing has gone faster yet, but because faster doesn't even make sense within the geometry of space-time. And this is also why time dilation matters so profoundly for particles like muons. A muon traveling at 99.95% of the speed of light is brushing up against this cosmic boundary. It's moving so close to the speed where time stops that its internal clock, from our perspective, has slowed to a crawl. The muon is experiencing time at a tiny fraction of the rate we experience it. Not because there's something special about the muon, but because it's moving through space-time at a speed where the geometry of the universe itself stretches time out enormously. All of this brings us back to the muon. A muon creates 15 kilometers above the Earth's surface, traveling at 99.95% of the speed of light, lives for only 2.2 microseconds in its own reference frame. But from our reference frame on the ground, time dilation stretches that lifetime enormously. The moon's clock is running slow relative to ours. Its 2.2 microsecond lifetime, as observed from the ground, becomes much longer, long enough for it to cross the entire depth of the atmosphere, long enough for it to reach the surface, long enough for it to pass through your body. The muon doesn't know it's living longer from our perspective. From its own perspective, it lives for exactly 2.2 microseconds, the same as always. But from our perspective, watching from the ground, that tiny lifespan gets stretched by the Lorentz factor into something far more substantial. And this stretching is what solves the mystery. This is why muons reach the ground. Not because they move faster than we thought. Not because they're created lower in the atmosphere than we thought. Not because they live longer in their own frame than we thought. But because time itself moves at different rates depending on your frame of reference. And from our frame of reference, the moon's brief life lasts long enough to make the trip. Einstein published his theory in 1905. Muons weren't discovered until 1936. The prediction came before the evidence. Einstein didn't know about muons when he worked out the mathematics of time dilation. He was thinking about light and motion and the fundamental nature of space-time. But the theory he built, from pure logic and two simple postulates, predicted exactly what would later be observed. Particles moving at close to the speed of light would appear to live longer when observed from a stationary frame. And when muons were discovered and their paradoxical survival was noticed, special relativity was already waiting with the answer. The mathematics had been done. The framework was in place. All that remained was to measure it, to confirm that the muons were indeed living longer from our perspective by exactly the factor that the Lorentz transformation predicted. And that confirmation, as we'll see, was spectacular. Now we come to the heart of the matter. So now we know the problem. Muons are created about 15 kilometers above the Earth's surface. They travel at roughly 99.95% of the speed of light. They live for about 2.2 microseconds. And classical arithmetic says they should disintegrate after traveling only about 660 meters. Yet they reach the ground in enormous numbers. And we know that moving clocks run slower as observed by a stationary observer, an effect that grows more dramatic as speed increases toward the speed of light. Now it's time to put these two pieces together and actually walk through the numbers. Because when you do the math, when you actually calculate what time dilation does to a muon traveling at these speeds, the result is stunning. Everything falls into place with breathtaking precision. The mystery dissolves completely. But here's what makes this particular example so powerful and so beautiful. There are actually two different ways to explain why the muon survives. Two completely different stories, told from two completely different perspectives. One story is told from the perspective of someone standing on the ground watching the muon come down. The other story is told from the perspective of the muon itself. These two stories sound like they should contradict each other. They use different mechanisms, they invoke different effects, but they arrive at exactly the same conclusion. The muon reaches the ground, and the fact that both stories agree, despite being so different, is one of the most elegant demonstrations of the internal consistency of Einstein's theory of special relativity. Let's start with the story as told from the ground. You're standing at sea level with a particle detector. You look up. 15 kilometers above your head, a cosmic ray collision has just created a muon. The muon is heading straight down towards you at 99.95% of the speed of light. From your perspective on the ground, the muon is moving incredibly fast. And because it's moving so fast, time dilation applies. The muon's internal clock is running slower than your clock. How much slower? That depends on the Lorentz factor, gamma, which is determined by the muon's speed. At 99.95% of the speed of light, gamma works out to approximately 31.6. You don't need to know the formula to understand what this means. It means that from your perspective on the ground, every process inside the muon is happening 31.6 times slower than it would if the muon were sitting still in front of you. The muon's internal decay clock, the process by which it transforms into an electron and two neutrinos, is running 31.6 times slower than normal. The muon's proper lifetime is 2.2 microseconds. That's how long it lives in its own rest frame. But from your perspective on the ground, because time dilation is stretching the muon's time, its apparent lifetime is 2.2 microseconds multiplied by gamma. 2.2 times 31.6 gives you roughly 69.5 microseconds. Let's round that to about 70 microseconds. From your perspective, the muon appears to live for about 70 microseconds instead of 2.2. That's more than 30 times longer than its proper lifetime. Now let's check whether 70 microseconds is enough time for the muon to reach you. The muon is traveling at 99.95% of the speed of light, which is approximately 299,850,000 meters per second. Multiply that speed by 70 microseconds, which is 70 millionths of a second, or 0.00007 seconds. The distance comes out to approximately 21,000 meters, 21 kilometers. The muon needs to travel only 15 kilometers to reach you from its creation altitude. And we've just calculated that in its dilated lifetime, it can travel about 21 kilometers. 15 is well within 21. The muon makes it, with room to spare. This is the Earth frame explanation. From the ground observer's perspective, the muon survives because time dilation stretches its lifetime from 2.2 microseconds to roughly 70 microseconds, giving it more than enough time to cross 15 kilometers of atmosphere at nearly the speed of light. The math works out perfectly. The predicted muon flux at ground level, calculated using time dilation, matches what detectors actually measure. The mystery is solved. But now let's tell the other story. Let's jump into the muon's reference frame and see what the journey looks like from its own perspective. This is where things get really interesting. From the muon's own point of view, it is not moving. This might sound strange, but remember Einstein's first postulate. The laws of physics are the same in all inertial frames. The muon is in an inertial frame, moving at constant velocity in a straight line through the atmosphere. From its own perspective, it's perfectly entitled to consider itself stationary. In the moon's frame, it is the Earth that is rushing upward toward it at 99.95% of the speed of light. The muon is sitting still, and the entire planet, atmosphere and all, is hurtling toward it at tremendous speed. From the moon's perspective, its lifetime is exactly 2.2 microseconds. There is no time dilation in its own frame. Time passes normally for the muon. Its internal clock ticks at the regular rate. It has 2.2 microseconds to live, and that's that. No stretching, no slowing, just 2.2 microseconds of existence. So how does the muon reach the ground in only 2.2 microseconds? If the ground is 15 kilometers away, and the muon only has 2.2 microseconds, even at nearly the speed of light, we already calculated that it can only travel about 660 meters in that time. 15 kilometers is way too far. The answer lies in a different consequence of special relativity. Not time dilation, but something equally strange and equally real. Length contraction. When an object is moving relative to you at a significant fraction of the speed of light, the distances in the direction of motion are compressed. They get shorter. Not because something is physically squeezing them, but because of the way space and time are intertwined in Einstein's framework. Space itself, measured from one reference frame, is shorter in the direction of motion when viewed from another frame moving at high speed. The amount of contraction is determined by the same Lorentz factor gamma. If gamma is 31.6, then distances in the direction of motion are contracted by a factor of 31.6. They shrink to 1/31.6th of their rest length. Now apply this to the muon's frame. In the muon's rest frame, the Earth and its atmosphere are rushing toward the muon at 99.95% of the speed of light. And because the Earth is moving at this speed relative to the muon, the distances along the direction of motion are contracted. The 15 kilometers of atmosphere between the muon's creation point and the ground, as measured from the ground, are not 15 kilometers in the muon's frame. They are 15 kilometers divided by gamma. 15,000 meters divided by 31.6 gives you approximately 475 meters. From the muon's perspective, the entire depth of the atmosphere between it and the ground is only about 475 meters. Not 15 kilometers, 475 meters. The atmosphere has been compressed, squished down to a thin layer. The Earth is rushing up at the muon, and the distance the Earth has to travel to reach the muon is only 475 meters. Can the Earth travel 475 meters in 2.2 microseconds at 99.95% of the speed of light? Let's check. The speed is approximately 299,850,000 meters per second. Multiply by 2.2 microseconds. You get about 660 meters. The Earth needs to travel only 475 meters to reach the muon, and we've just calculated that in 2.2 microseconds, the Earth, from the muon's frame, covers about 660 meters. 475 meters is well within 660 meters. The ground reaches the muon before the muon decays. It makes it. The muon survives. Take a moment to appreciate what just happened. We told two completely different stories about the same event. In the first story, told from the ground, the muon survives because time dilation stretches its lifetime. The distance stays the same at 15 kilometers, but the muon has much more time than the classical calculation suggests, because its clock is running slow from our perspective. In the second story, told from the muon's frame, the muon survives because length contraction compresses the distance it needs to cross. The lifetime stays the same at 2.2 microseconds, but the distance is much shorter than the classical calculation assumes, because the atmosphere is contracted from the muon's perspective. Different mechanisms, different explanations, but the same result. The muon reaches the ground. This is not a coincidence. This is the deep internal consistency of special relativity at work. Time dilation and length contraction are not separate, unrelated effects. They are two sides of the same coin. They are both consequences of the same underlying structure of space-time. In any situation where time dilation plays a role, length contraction plays a complementary role, and they always give the same physical prediction. You can analyze any relativistic situation from any valid reference frame using whatever combination of time dilation and length contraction applies in that frame, and you will get the same answer for what physically happens. The muon reaches the ground. That's a physical fact. It doesn't depend on which reference frame you use to describe it. What does depend on the reference frame is the explanation for how it happens. But the outcome is always the same. This is what physicists mean when they say the laws of physics are the same in all inertial frames. It doesn't mean every measurement is the same. Time intervals are different. Distances are different. Even the order of some events can be different in different frames. But the physical outcomes, the things that actually happen in the real world, are always the same. A muon either reaches the ground or it doesn't, and all frames agree on which one it is. Let me go through this one more time to make sure the contrast is completely clear, because this is worth understanding thoroughly. In the Earth frame, the atmosphere is 15 kilometers thick, and the muon lives for about 70 microseconds due to time dilation. Plenty of time to cross 15 kilometers at nearly the speed of light. In the muon frame, the muon lives for 2.2 microseconds, and the atmosphere is only about 475 meters thick due to length contraction. Plenty short enough to cross in 2.2 microseconds at nearly the speed of light. Same physics, same outcome, different descriptions. This dual explanation is often taught in physics classes as one of the best ways to understand the relationship between time dilation and length contraction. They're not independent phenomena. They're two perspectives on the same relativistic geometry of space-time. You can't have one without the other. If time dilation exists, length contraction must also exist. And vice versa. They come as a package deal, baked into the structure of space-time itself. If you accept that the speed of light is the same for all observers, which experiments have confirmed beyond any reasonable doubt, then you must accept both time dilation and length contraction. They follow inevitably from that single postulate. You don't get to choose one and reject the other. Nature gives you both, and both are equally real. Now, I want to address something that sometimes bothers people when they first encounter these ideas. People often ask whether time dilation and length contraction are real, or whether they're just some kind of measurement effect or optical illusion. This is a fair question, and it deserves a clear answer. They are absolutely unequivocally real. They are not illusions. They are not artifacts of measurement. They are not tricks of perspective. They are genuine physical effects that have measurable consequences in the real world. When we say the muon's lifetime is stretched to 70 microseconds in the Earth frame, we mean that the muon genuinely exists for 70 microseconds, as measured by clocks on the ground. If you line up a series of detectors along the muon's path, you will detect the muon at locations that require it to have been alive for much longer than 2.2 microseconds. The detectors are real. The signals they record are real. the muon was physically present at those locations. When we say the atmosphere is contracted to 475 meters in the muon's frame, we mean that if the muon could somehow carry a ruler, that ruler would measure the distance from the top of the atmosphere to the ground as 475 meters. This is not because the ruler is broken or because the muon is confused. It's because space-time itself has a geometry that makes distances genuinely shorter in the direction of motion for a moving observer. The difference between time dilation being real versus being an illusion is the difference between a stick that looks shorter because you're seeing it at an angle versus a stick that actually is shorter. In relativity, the effects are the second kind. They are actual physical changes in the relationships between events in space-time, depending on the observer's frame. If time dilation were just an illusion, the muons would not reach the ground. The whole point is that they do reach the ground. That's the evidence. The fact that we detect them at sea level in enormous numbers is proof that these effects are real. You can't explain the muon flux at ground level without time dilation or length contraction, or both. Any attempt to explain it using purely classical physics, where time is absolute and distances are the same for everyone, fails catastrophically. The classical prediction is off by a factor of billions. Only relativity gives the correct answer. There's another subtle point worth exploring here. You might wonder whether the muon actually experiences anything unusual. The answer is no. From its own frame, everything is perfectly normal. It exists for 2.2 microseconds. The atmosphere is 475 meters thick. It crosses that distance and hits the ground. Nothing strange happens from its perspective. The strangeness only appears when you compare measurements between different frames and try to reconcile them with your everyday intuition. Your intuition says that time should be the same for everyone, and distances should be the same for everyone. Relativity says neither of those things is true. A reference frame is not a physical thing. It's a way of describing events, like choosing a language to tell a story. The story doesn't change, the events don't change, but the description is different. The muon is created at a certain point in space-time. It travels along a certain path. It arrives at the ground, another point in space-time. These events are fixed. What changes between frames is how you describe the intervals between these events, how much time passes and how much distance is covered. In the Earth frame, the time interval is long and the distance is 15 kilometers. In the muon frame, the time interval is short and the distance is 475 meters. But both frames describe the same two events, creation and arrival, and both agree that the second event happens. The muon reaches the ground. Let me push the numbers a little further to show how precisely this all works. I've been using 99.95% of the speed of light as the muon's typical speed. But muons created in the atmosphere actually come in a range of speeds depending on the energy of the original cosmic ray that triggered the cascade. Some muons are faster, some are slower. This means different muons experience different amounts of time dilation. A muon traveling at 99% of the speed of light has a Lorentz factor of about 7.1. Its dilated lifetime as seen from the ground would be about 2.2 times 7.1, which is roughly 15.6 microseconds. At 99% of light speed, the muon is moving at about 297 million meters per second. In 15.6 microseconds, it could travel roughly 4,630 meters. That's about 4.6 kilometers. A muon created at 15 kilometers altitude and moving at 99% of the speed of light would not make it to the ground. It would decay after about 4.6 kilometers, still more than 10 kilometers above the surface. And indeed, slower muons are less likely to reach the ground. Detectors at sea level see fewer muons at lower energies, because those slower muons don't get enough time dilation to survive the full trip. Now consider a muon at 99.99% of the speed of light. Gamma at that speed is about 70.7. Its dilated lifetime from the ground frame is 2.2 times 70.7, which is roughly 155 microseconds. At this speed, it could travel about 46.6 kilometers before decaying. That's far more than enough to traverse the full atmosphere. These muons arrive at sea level with ease. In the muon's own frame at 99.99% of light speed, the atmosphere would be contracted from 15 kilometers down to about 212 meters. The muon traverses that distance easily in its 2.2 microsecond lifetime. The key insight is that the survival rate of muons at ground level depends on their speed and therefore on the amount of time dilation they experience. Faster muons get more time dilation, survive longer from the ground, perspective, experience more length contraction, and are much more likely to reach the surface. Slower muons get less time dilation, less length contraction, and are more likely to decay before they arrive. This speed dependence is itself a testable prediction. If time dilation is real, you should see a specific relationship between muon speed and survival rate. Faster muons should survive at higher rates in a way that precisely matches the Lorentz factor predictions. And that is exactly what experiments find. The measured survival rates of muons at different speeds match the relativistic predictions with extraordinary precision. If time dilation didn't exist, if classical physics were correct, the survival rate would be essentially the same pathetically low number, regardless of speed, because even at 99.99% of the speed of light, the classical calculation gives you only about 660 meters of travel before decay. The classical prediction doesn't care about the exact speed, because even the fastest muons can't classically survive 15 kilometers. But the data shows a clear, dramatic dependence on speed that matches the Lorentz factor curve perfectly. There's something deeply satisfying about this. The same theoretical framework that was built in 1905 to explain the constancy of the speed of light and the symmetry of physical laws between reference frames also turns out to perfectly predict the survival rate of particles that wouldn't be discovered for another 3 decades. Einstein didn't design special relativity to explain muon survival. He didn't know muons existed. He was thinking about light and motion and the logical consequences of 2 simple postulates. But the theory he built was so fundamentally correct, so deeply woven into the actual structure of reality, that it automatically predicted phenomena that hadn't even been observed yet. This is one of the hallmarks of a great physical theory. It doesn't just explain the things it was designed to explain. It reaches beyond its original scope and correctly predicts entirely new phenomena. Special relativity was built to resolve the puzzle of the constant speed of light. But it also predicted time dilation, length contraction, the equivalence of mass and energy, the impossibility of faster than light travel, and countless other effects that have all been confirmed. The muon's survival is just one of those confirmations, but it's one of the most vivid and direct. You don't need a particle accelerator to see it. You don't need sophisticated equipment. Muons are raining down on you right now, having survived a journey that is only possible because time runs at different rates in different reference frames. Every muon that hits your body is a tiny piece of evidence for the reality of time dilation. What makes the muon case so compelling is its directness. Many confirmations of relativity involve extremely precise measurements of very small effects. Atomic clocks on airplanes, corrections to GPS signals, tiny shifts in the orbits of planets. These are all real and important, but they involve small deviations from classical predictions. The muon case is different. It's not a small deviation. It's an all-or-nothing situation. Without time dilation, essentially no muons reach the ground. With time dilation, thousands per square meter per minute reach the ground. The difference is not a subtle correction. It's the difference between silence and a flood, between nothing and everything, between a prediction of 0 and an observation of 10,000 per square meter per minute. You can't fudge this. You can't explain it with a small adjustment to classical physics. You can't invoke some minor overlooked factor that changes the answer by a few percent. The discrepancy between the classical prediction and the observed reality is so enormous that nothing short of a fundamental revision of our understanding of time can account for it. And special relativity provides exactly that revision. It doesn't just nudge the numbers in the right direction, it gives you the exact answer, correct to within the precision of our best measurements. The muon's journey through the atmosphere is not just evidence for time dilation. It's one of the most dramatic and unambiguous confirmations of any prediction in all of physics. A particle that should die in the sky reaches the ground by the thousands. Time itself bends to make it possible. And two completely different stories, one about stretched time and one about compressed distance, told from two completely different perspectives, converge on the same extraordinary conclusion. The muon survives. Not because our physics is wrong, but because our old intuitions about time and space were incomplete. The universe operates according to rules that are stranger and more beautiful than anything our everyday experience could have prepared us for. And a tiny, short-lived, almost invisible particle, born in violence at the top of the atmosphere and dead before you could blink, carries the proof in its very survival. Everything up to this point has been conceptual. We've built the logic, walked through the math from two different reference frames, and shown that both give the same physical result. But science isn't built on logic alone. It isn't built on elegant mathematics or beautiful thought experiments. Science is built on evidence, on measurements, on experiments that can be repeated and verified and scrutinized by anyone with the right equipment. A theory can be as mathematically perfect as you like. If it doesn't match the data, it's wrong. So the question we need to answer now is this: has anyone actually tested whether muon survival matches the predictions of special relativity? Has anyone gone out into the real world, counted muons at different altitudes, measured their speeds, tracked their decay rates, and compared the results to what Einstein's theory predicts? The answer is yes, many times, with increasing precision over the decades. And the results are spectacular. The most famous of these experiments was conducted in 1963 by two physicists at the Massachusetts Institute of Technology, David Frisch and James Smith. Their experiment was elegant in its simplicity. The basic idea was straightforward. Go to a high altitude and count the number of muons arriving there. Then go to sea level and count the number of muons arriving there. Compare the two numbers. See if the difference matches what special relativity predicts or what classical physics predicts. If classical physics is right, almost all the muons detected at high altitude should decay long before reaching sea level. The number at the bottom should be nearly zero compared to the number at the top. If special relativity is right, many more muons should survive to sea level, because time dilation extends their observed lifetimes. The number at the bottom should be much higher than the classical prediction, and it should match the specific value calculated using the Lorentz factor. Frisch and Smith chose Mount Washington in New Hampshire as their high-altitude location. The summit of Mount Washington sits at an altitude of about 1,900 meters, roughly 6,280 feet above sea level. This isn't as high as the 15 kilometers where moons are initially created, but it's high enough to make a meaningful measurement. They set up muon detectors at the summit and carefully counted the number of moons arriving per hour within a specific speed range. They focused on moons traveling at about 99.5% of the speed of light, which corresponds to a Lorentz factor of about 10. They measured how many muons in that speed range arrived at the top of Mount Washington per hour. Then, they moved their equipment down to Cambridge, Massachusetts, essentially at sea level, and repeated the measurement. Same detectors, same speed range, same methodology, just a different altitude, roughly 1,900 meters lower. Now, here's what classical physics would predict. A muon traveling at 99.5% of the speed of light moves at roughly 298,500,000 meters per second. At that speed, it takes about 6.4 microseconds to travel 1,900 meters, the altitude difference between the summit and sea level. The muon's mean lifetime is 2.2 microseconds. So, 6.4 microseconds represents roughly 2.9 muon lifetimes. After 2.9 lifetimes, the fraction of surviving muons should be about 5.4%. For every 100 muons counted at the top, only about 5 should survive to sea level, according to classical physics. But special relativity predicts something very different. At 99.5% of the speed of light, gamma is about 10. Time dilation stretches the muon's apparent lifetime from 2.2 microseconds to about 22 microseconds as seen from the ground. The travel time of 6.4 microseconds now represents only about 0.29 muon lifetimes in the dilated frame. After 0.29 lifetimes, the surviving fraction should be about 75%. For every 100 muons counted at the top, about 75 should survive to sea level. The difference between these two predictions is enormous. Classical physics says about 5 out of every 100 muons should survive. Relativity says about 75 out of every 100 should survive. That's not a subtle difference. It's a factor of 15. Any competent experiment should easily distinguish between these predictions. And Frisch and Smith's experiment did exactly that. At the summit of Mount Washington, they detected roughly 563 muons per hour in their target speed range. At sea level, they detected roughly 408 muons per hour. The survival rate was about 72%, not 5% as classical physics predicted. 72%, almost exactly what special relativity predicted. The agreement with the relativistic prediction was remarkable. The small difference between the measured 72% and the predicted 75% was well within the experimental uncertainties. The data matched Einstein's theory almost perfectly, and it demolished the classical prediction completely. This single experiment, performed with relatively simple equipment in 1963, provided one of the clearest and most direct confirmations of special relativistic time dilation ever achieved. Frisch and Smith even made a film about their experiment, which was used in physics education for decades. The film showed their equipment, their methodology, their data, and their analysis. It became one of the most well-known physics demonstration films ever produced. What made their experiment so powerful was its directness. There was no ambiguity, no complex chain of reasoning, no need to invoke multiple theories or make long lists of assumptions. They counted muons at the top of a mountain. They counted muons at the bottom. The ratio matched relativity and contradicted classical physics. The evidence was as straightforward as science gets. But the Frisch-Smith experiment was just the beginning. In the decades since, muon time dilation has been confirmed with far greater precision using particle accelerators. In these experiments, physicists don't have to rely on naturally occurring cosmic ray muons, whose speeds and creation points are somewhat uncertain. Instead, they create muons in controlled conditions, accelerate them to precisely known speeds, and measure their lifetimes with extraordinary accuracy. The most precise of these experiments have been conducted at major particle physics laboratories, like CERN in Geneva, Switzerland, Brookhaven National Laboratory on Long Island, New York, and Fermilab near Chicago, Illinois. At these facilities, muons are produced by slamming protons into targets, creating pions, which then decay into muons. The muons are injected into storage rings, circular paths where powerful magnets keep them circulating at known speeds. As the muons travel around the ring, they gradually decay. Detectors positioned around the ring count the decay products. Electrons or positrons, depending on the muon's charge, that fly off each time a muon decays. By tracking how the number of surviving muons decreases over time, physicists can measure the muon's lifetime at that particular speed with extreme precision. The results of these storage ring experiments are stunning. At Brookhaven National Laboratory, the muon G-2 experiment has measured the lifetime of muons, circulating at 99.94% of the speed of light. At this speed, the Lorentz factor is about 29.3. The predicted dilated lifetime is about 2.2 microseconds, times 29.3, which is about 64.5 microseconds. The measured dilated lifetime matches this prediction to within a fraction of a percent. The agreement between theory and experiment is not approximate. It's precise. Extraordinarily precise. The Lorentz factor has been verified for muons to an accuracy of better than 1 part in 1,000 in these experiments. That means if you calculate the expected lifetime dilation using Einstein's formula and compare it to the measured lifetime dilation, the two numbers agree to better than 0.1%. This is the kind of precision that leaves no room for alternative explanations. No other theory that has ever been proposed can match these measurements. Classical physics predicts the wrong answer by a factor of many times over. Every proposed modification to relativity that has ever been suggested either gives the same answer as Einstein's theory in this regime, in which case it's not really a different theory, or it gives a different answer that doesn't match the data. Special relativity remains the only framework that correctly predicts the measured lifetimes of high-speed muons. But muon experiments are far from the only evidence for time dilation. The effect has been confirmed by dozens of independent methods across many different areas of physics. Each one on its own would be strong evidence. Together they form an overwhelming case that time dilation is a real, physical property of the universe. In 1971, two physicists named Joseph Hafele and Richard Keating conducted one of the most famous experiments in the history of physics. They placed 4 cesium beam atomic clocks on commercial airplanes and flew them around the world. One set of flights went eastward, another set went westward. When the flights were over, they compared the airborne clocks to identical clocks that had remained on the ground at the United States Naval Observatory in Washington, D.C. The results matched the predictions of relativity. The eastward flying clocks, which were moving faster relative to the Earth's center due to adding the plane's speed to the Earth's rotation, lost about 59 nanoseconds compared to the ground clocks. The westward flying clocks, which were effectively moving slower relative to the Earth's center, because the plane's speed partially cancelled the Earth's rotation, gained about 273 nanoseconds. These numbers included both the special relativistic effect of speed and the general relativistic effect of altitude, since the planes were also higher up in Earth's gravitational field, where time runs slightly faster according to general relativity. Both effects were measured simultaneously, and both matched Einstein's predictions. The Hafele-Keating experiment was groundbreaking because it used real clocks on real airplanes flying real routes. There was nothing exotic about the setup. These were commercial flights with paying passengers. The physicists simply brought atomic clocks aboard as carry-on luggage, and when the flights were over, the clocks told a story that Newton's physics could never have predicted. Time had passed at different rates for the traveling clocks and the stationary clocks, not by much, nanoseconds, but the differences were real, measurable, and exactly what Einstein's equations predicted. The global positioning system provides what might be the most practical and ubiquitous confirmation of time dilation. GPS relies on a constellation of satellites orbiting Earth at an altitude of about 20,200 kilometers. Each satellite carries an atomic clock that broadcasts precise time signals. Your phone or GPS receiver picks up signals from multiple satellites, compares the arrival times, and calculates your position based on the differences. For this to work, the satellite clocks need to be extraordinarily accurate. Any error in the clocks translates directly into an error in position. An error of just 1 microsecond in timing corresponds to a position error of about 300 meters, because light and radio signals travel about 300 meters in 1 microsecond. The GPS satellites are moving at about 14,000 kilometers per hour relative to the ground. This means special relativistic time dilation causes their clocks to tick slightly slower than ground clocks by about 7 microseconds per day. At the same time, the satellites are higher up in Earth's gravitational field, where gravity is weaker. General relativity predicts that clocks in weaker gravitational fields tick faster. This general relativistic effect causes the satellite clocks to tick faster by about 45 microseconds per day. The net effect is that GPS satellite clocks tick about 38 microseconds per day, faster than ground clocks. 38 microseconds per day might sound insignificant, but remember, 1 microsecond corresponds to about 300 meters of position error. 38 microseconds per day would mean an accumulated position error of about 11.4 kilometers per day. Within a week, your GPS would be off by 80 kilometers. Within a month, it will be useless. To prevent this, the GPS system applies relativistic corrections to every satellite clock. These corrections account for both special and general relativistic time dilation. They are programmed into the satellite software and applied continuously. Every time you use GPS to navigate, every time your phone tells you where you are, every time a delivery driver finds your address or a pilot lands an airplane using GPS guidance, the system is silently correcting for the fact that time passes at different rates, at different altitudes and different speeds. You are using relativity every single day. You just don't realize it. There are other confirmations as well. Particle accelerators around the world routinely observe time dilation for many different types of unstable particles, not just muons. Pions, kaons, hyperons, and many other short-lived particles all show extended lifetimes when traveling at high speeds, and the extensions always match the Lorentz factor predictions. In 2010, researchers at the National Institute of Standards and Technology in Boulder, Colorado, used the most precise clocks ever built, optical atomic clocks accurate to within a few seconds over the age of the universe, to measure time dilation at everyday scales. They showed that raising one clock just 33 centimeters, about a foot, above another identical clock, caused the higher clock to tick faster by a measurable amount. They also showed that a clock moving at a speed of less than 10 meters per second, about the speed of a brisk jog, ticked slower than an identical stationary clock. These are relativistic effects measured at human scales, with human speeds and human distances. The effects are unimaginably tiny, fractions of a second accumulated over millions of years. But they're there, they're real, and they match Einstein's predictions exactly. In 2014, scientists used the European Space Agency's Galileo satellites to perform one of the most precise tests of gravitational time dilation ever conducted. 2 satellites were accidentally launched into elliptical orbits instead of the planned circular orbits. Rather than treating this as a failure, physicists realized it was an opportunity. As the satellites moved closer to and farther from Earth in their elliptical paths, their clocks experienced different amounts of gravitational time dilation. By comparing the satellite clocks to ground clocks over many orbits, the researchers confirmed general relativistic time dilation to a precision of about 2 parts in 100,000. The accidental orbit turned into one of the best tests of relativity ever performed. Every single one of these experiments, from Frisch and Smith counting muons on Mount Washington in 1963, to NIST measuring clock differences across 33 centimeters in 2010, tells the same story. Time is not absolute. It does not tick at the same rate for everyone. It depends on how fast you're moving and how deep you are in a gravitational field. And the specific way it depends on these things is precisely, to extraordinary accuracy, what Albert Einstein predicted in 1905 and 1915. There is no wiggle room here, no ambiguity, no alternative interpretation that fits the data equally well. Time dilation is real, it is measured, it is confirmed, and it is used in technology that billions of people depend on every day. And here is something that brings this whole story full circle in a way that might surprise you. The muon, this particle whose impossible survival once baffled physicists, whose journey through the atmosphere only makes sense because of relativistic time dilation, has become a practical tool precisely because it reaches the ground. Scientists have turned the muon's paradoxical survival into a technology. It's called muon tomography, and it works on a beautifully simple principle. Muons rain down from the sky constantly, and they pass through almost everything. But different materials slow them down, scatter them, or absorb them at different rates. Dense materials like LED, uranium, or solid rock absorb more muons than less dense materials like air, water, or empty space. If you place muon detectors around or beneath an object and carefully track which muons make it through and which don't, you can build up a picture of the object's internal structure without ever cutting it open. It's like taking an X-ray, but instead of using a machine to generate radiation, you're using the natural rain of cosmic ray muons from the sky. And because muons are far more penetrating than X-rays, they can image objects that are far too large or too dense for any conventional scanning technology. In 2017, physicists working on a project called Scan Pyramids used muon tomography to peer inside the Great Pyramid of Giza in Egypt. This is a structure that has stood for roughly 4,500 years. It's made of approximately 2.3 million stone blocks, each weighing several tons on average. You can't X-ray a pyramid. You can't cut it open to look inside, but you can let cosmic ray muons rain down through it and measure how many come out the other side. Researchers placed muon detectors inside known chambers deep within the pyramid and recorded the muons arriving from every direction over a period of months. Where the pyramid was solid stone, fewer muons made it through. Where there was empty space, more muons arrived. By analyzing the patterns, the team discovered a large, previously unknown void above the Grand Gallery. This void is at least 30 meters long, a significant empty space hidden inside the pyramid for thousands of years that no one knew existed. The muons revealed it without disturbing a single stone. The same technique has been used to image the interiors of volcanoes. Scientists have placed muon detectors on the flanks of active volcanoes and used the natural muon flux to map the density structure inside. They can see where magma chambers are located, where rock is dense and solid, and where pockets of gas or fluid exist. This information is critical for predicting eruptions and understanding volcanic behavior. Muon tomography has also been used to inspect the damaged nuclear reactors at the Fukushima Daiichi power plant in Japan. After the disaster in 2011, the reactor cores melted down and the interiors became far too radioactive for any human to enter. Robots struggled in the extreme radiation environment, but muons, raining down from the sky, pass through the reactor buildings just as they pass through everything else. By placing detectors around the reactor buildings and tracking the muon paths, engineers were able to determine the location and distribution of the melted fuel inside the reactors without ever sending a person or even a camera inside. They could see where the dense nuclear material had pooled and settled. This information was essential for planning the decades-long cleanup effort. There is something deeply poetic about this. A particle that once puzzled physicists because it survived a journey it shouldn't have, a particle whose very existence at ground level is proof that time bends for objects moving near the speed of light, is now being used to see inside pyramids, volcanoes, and nuclear reactors. The mystery became the tool. The paradox became the technology. Let's step back now and appreciate the full picture. A proton expelled from a supernova millions of years ago arrives at Earth by pure chance and slams into a nitrogen nucleus 15 kilometers above your head. The collision creates a shower of pions. those pions decay into muons. One of those muons is heading straight down toward you at 99.95% of the speed of light. Classical physics says it should die after 660 meters, more than 14 kilometers above the ground. But from your perspective, time dilation stretches its 2.2 microsecond lifetime to roughly 70 microseconds, long enough to cover the full distance. From the muon's perspective, length contraction compresses 15 kilometers of atmosphere down to 475 meters, short enough to cross in its brief life. Both stories agree. The muon reaches the ground. It passes through the roof above your head, through your body, through the floor, and into the earth below. Thousands of them every single minute, surviving a journey that classical physics says is impossible. The Frisch-Smith experiment confirmed this in 1963. Storage ring. Experiments have confirmed it to extraordinary precision since. Atomic clocks on airplanes, GPS satellites, and optical clocks measuring across the span of a single foot all tell the same story. The evidence is overwhelming, unambiguous, and consistent across every experiment ever performed. What does all of this mean? What should you take away from the story of a tiny particle that dies in 2 millionths of a second, but somehow reaches the ground? At the most basic level, it means that the universe does not work the way your everyday intuition suggests. You live your life in a world where speeds are slow compared to light, where time seems absolute and universal, where distances are the same for everyone. These assumptions work perfectly well for driving your car, catching a ball, or walking to the store, but they are approximations. They are simplifications that work only because you're moving so slowly. When objects approach the speed of light, those approximations break down completely. Time becomes elastic. Distances become flexible. The rigid framework of absolute space and absolute time that seems so solid and obvious in everyday life turns out to be an illusion. The true nature of the universe is far stranger and far more beautiful. Space and time are not separate, independent things. They are woven together into a single fabric called space-time. And this fabric stretches and compresses and warps depending on how fast you're moving and how much gravity is present. This isn't philosophy. It isn't metaphor. It's measured, quantified, confirmed, and relied upon by technology you use every day. Every muon that passes through your body is a messenger from this deeper reality. Each one carries a simple but profound message. Time is not what you think it is. The universe is more flexible, more surprising, and more deeply interconnected than everyday experience could ever reveal. And we know this not because a genius told us so, though a genius did tell us so in 1905, but because we've measured it. We've counted the particles, we've compared the clocks, we've done the experiments, and the universe has answered clearly, consistently, and unmistakably. Time slows down for things that move fast. The faster they move, the more time slows. And a particle that lives for barely 2 millionths of a second, born in a violent collision high in the atmosphere, riding the edge of the speed of light, survives a journey of 15 kilometers through the sky to reach the surface of the Earth. It's happening right now, thousands of times per minute, through every square meter of the planet, through the mountains and the oceans and the cities and the fields, through you. Each one of those muons is a tiny, silent, invisible proof that Albert Einstein was right. That time is relative, that the universe is stranger than it looks, and that even the smallest, most short-lived particle can carry one of the deepest truths in all of physics. The next time you're outside on a clear night, looking up at the stars, remember that the sky above you is alive with moons, created in violence, traveling at nearly the speed of light, living and dying in microseconds, and surviving a journey that only makes sense because time itself bends for them. They're passing through you right now. They always have been. And now you know why.